Okay, it's a great pleasure to have Sam Garratt as our speaker for the last seminar of this seminar series this semester. And we will continue next semester. So Sam is a postdoc at Princeton, and I guess as many of you already know, he has done a lot of interesting work in quantum many-body physics, in particular focusing on non-equilibrium dynamics, quantum chaos, complexity, and so on. Today, he's telling us about uh, his new result about the entanglement structure of quantum many-body systems. Sam, please go ahead.
Yeah, thank you very much for the introduction and for the invitation to speak. I'll be talking about some new work that I posted on the archive yesterday. It appeared last night. This is a collaboration with Dima Rabbani, and it's something we've been up to in Princeton and other locations around the world where we ran into each other over the last few months. So let me start by motivating the problem. So this talk is about many-body quantum physics, and there are, of course, a huge number of mysteries in many-body quantum physics that have survived for quite a long time. These range from the nature of the strange metal phase identified in the cuprates decades ago, to the behavior of gauge theories at finite fermion densities, and the possibility of phase transitions in QT phase diagrams. So, these problems have been around for a while, so we have to ask ourselves why it is that they've survived for so long. And the problem, of course, is that if you take a many-body quantum system and you try to describe it on your computer, you're going to run into problems. And the reason is that an exact simulation of a quantum system of many particles requires an amount of memory on a classical computer that grows exponentially with the number of particles. So this problem is pretty ancient and very well known, and led decades ago to the idea of quantum simulation. So I probably don't need to tell the audience that the idea is that you take some highly controllable quantum system, many platforms are available now, and you use that highly controllable quantum system to simulate another system that you care about for some other reason. Maybe you believe that you have a model for what's going on in the cuprates, and you want to use your quantum simulator to check if your model agrees with your experiment. So this was the sort of dream in the early 80s that continues to this day. But also, since the 80s, we've developed a much clearer understanding of what it is that makes many-body quantum systems hard to simulate. In part, this is due to the introduction of ideas from information theory. So now that we have a much clearer understanding of what it is that makes classical computation hard, it's really time to kind of look back and ask, when is it that we really need quantum simulation to describe many-body systems? So let's home in on a kind of small subset of all the possible quantum simulation problems that you might care about, but nevertheless, a family that has a lot of practical relevance. So often when we're trying to understand the behavior of condensed matter systems, or any system of many interacting particles, the quantum phenomena are often most pronounced as you go to the lowest possible temperatures. And so we often understand what's going on by appealing to this idealized limit of zero temperature. The thing is that if we're trying to understand what's going on in this idealized limit of zero temperature, then we can often get away with a tensor network simulation. And this is because low temperature, low energy quantum states, ground states, I should say, are expected to not be so entangled. So I should add, please stop me at any point through the talk if you have a question. So let me say a bit more on this point about ground state entanglement. So throughout this talk, let's, for simplicity, focus in on spin systems arranged in kind of regular lattices, always geometrically local. So each of these gray circles represents a spin. And L here is the system's linear extent. So first off, suppose that you had a many-body Hamiltonian that had a spectral gap. So some finite gap between the ground and first excited state that survived as you went to the thermodynamic limit. So in this situation, we typically expect ground states to have a so-called area law of entanglement. Okay, that's to say that if I compute the entanglement entropy of half of the system, the amount of entanglement is basically just coming from short-range correlations across the so-called entanglement cut here between the blue and the white regions. So this area law is it's been proven for translation invariant systems in one spatial dimension. And it's conjectured to hold much more generally. So that's gap systems. Although many of the kind of most interesting phenomena arise in gapless regimes at quantum critical points. There, as the gap closes, what one typically finds is that the entanglement in the ground state increases. So, for example, in one spatial dimension, whereas in a gapped phase you'd expect constant entanglement of half the system, in a gapless phase in 1D with dynamic critical exponent 1, you instead expect to violate this area law by some logarithm of the system size. So going beyond 1D, for example, looking at a metal in 2D or 3D, then what one expects is that the half system entanglement entropy scales not with an area law, but with an area law with a multiplied by a logarithm. Okay, so you get this multiplicative logarithmic correction. But what I want to highlight is that in both of these settings, gapped or gapless, the ground state is not that highly entangled. It's area law with a log violation kind of at worst, at least in the models of condensed matter that we consider to be physical, whatever that means. So let me say a little bit more about entanglement, the entanglement of generic states, and also what this entanglement, what this low entanglement of ground states buys us in the way of simulations. So first off, if I had a generic quantum state, the amount of memory I would need to write it down in a classical computer would be exponential in volume rather than exponential in volume. And partially, we can understand this from the fact that the half system entanglement entropy follows a volume law rather than an area law with some correction. So on the other hand, if we can write down our quantum state as a tensor network, and that's a kind of big if in some situations, then if your tensor network has some bond dimension chi, the memory you need to write down your state is just going to scale as the number of degrees of freedom multiplied by some power of chi. So coming back to what I was saying a moment ago, the area law in translation invariant 1D quantum systems carries over to the sort of lower Renyi entropies. I'll say more on those later. And you can get away with an approximation to this state using a tensor network that has finite bond dimension. Even if you go to a quantum critical state, the bond dimension you need is only going to be polynomial in the system size. So you get away with a description of your state that requires polynomial memory rather than exponential memory. And we also, in many cases, expect tensor networks to accurately describe 2D ground states and or even weakly entangled states in 1D and actually also in 2D. There are many numerical demonstrations that tensor networks do pretty well. Okay, so this looks like very bad news for quantum simulations at zero temperature. If we can get away with describing our ground states and lowest excited states using tensor networks, then we'd probably just build better classical computers. But the thing is that we also know of certain ground states of local Hamiltonians that are highly entangled. So the existence of these highly entangled ground states shows us that the ground state problem is, worst case hard for tensor networks. So to give you a few examples, they're all fairly detailed constructions. There's some work going back really quite a long time to Sandy Irani, who showed back in 2009 that there are translation invariant 1D Hamiltonians. So they're slightly strange. They're families of one-dimensional Hamiltonians, but the terms in the Hamiltonian depend on the length of the system. And there you find volume law entanglement in the unique ground state. There are also the so-called Motzkin and Fredkin chains, where you find a violation of the area law not by log L, but by square root L. There are generalizations of that construction to two spatial dimensions, where one finds a volume law entanglement. And recently, David Long and Matteo Ippoliti have shown how the circuit to Hamiltonian construction can be used to construct local Hamiltonians in 1D that have volume law entanglement. Okay? So exactly what it is that separates these systems from what we often think of as generic quantum systems is not extremely clear. And resolving this question is going to be one of the aims of this talk.
So just to make sure, are these all gapless?
They are all gapless.
Uh-huh. But is it also possible to have a family of translation invariant Hamiltonians where the local terms in the Hamiltonian depend on the system size in a way that maybe the Hamiltonian density in this sequence of systems is unbounded. And suppose in that case, somehow the ground state is still gapped, but is it still possible to violate the area law?
This is a very good question. I think I'd have to think about it for a very long time before coming back with a clear answer to that one, unfortunately. The first I should stress though that the Hamiltonians that were found back in 2009 are perhaps the strangest ones here. So a more kind of sensible looking Hamiltonian arises in the second line here. So they're colored Motzkin and Fredkin chains. So these are gapless, but they just look like ordinary, almost translation invariant spin chains. So, but I think what we learned from all of this is it is certainly possible to construct local Hamiltonians that have very strangely behaved ground states.
Mhm.
So your suggestion may be realized in some Hamiltonian, but I'd have to think about it. Thanks for the
Mhm.
question.
So just to make sure, so for the only in the first case, the local terms have dependence on L, but in the other three cases, they don't depend on the system size?
They don't depend on the system size, but they do depend on boundary conditions, as I will discuss in great detail later in this talk.
Thanks.
Okay. Yeah, thanks for the questions. So, okay, so to summarize where we are so far, we typically expect ground states of local Hamiltonians to be pretty weakly entangled. But people have gone out of their way to construct these Hamiltonian to, show us that that intuition is too naive, and that there are, in fact, local Hamiltonians whose ground states are highly entangled. So this is the kind of key question that I want to address. When is it that quantum systems are weakly entangled at low energies? So what I'm going to show you today is how is it's the solution to a mathematical problem where you take a geometrically local Hamiltonian and you suppose you have a pure quantum state that has a fixed energy expectation value with respect to that Hamiltonian. So what I'm going to show you is that the entanglement entropy of any pure quantum state of a many-body system with fixed energy expectation value can be upper bounded by a sum of thermal entropies. And this is going to give us a very useful mapping to thermodynamics, which will essentially reveal to us that having well-behaved thermodynamic properties is enough to give you low entanglement at low energies. So, brief outline is as follows. So, first off, I'll show you quickly how to derive this bound. It doesn't take too much time. Um, After this, I'll give you some examples of relations between thermodynamics and low energy entanglement. Some very interesting early work on this from about a decade ago from Fernando Brandao and also from Brian Swingle and their collaborators. And I'll describe some kind of key technical differences between what was done there and what I'm doing today. And that's going to be very important for the last part of the talk, where I'm able to say the most. And there I'll be focusing on frustration-free systems.
Hi, Sam. Like, just a quick question. So the entanglement entropy is just a function of the state itself, right? Independent of however you realize it. So the SA of psi is just a function of the state, but are you saying that you can use information about some local Hamiltonian on the left-hand side to bound it?
Yeah, yeah, right. So the state, so I'm considering the family of all states that have fixed energy expectation value, E, with respect to a Hamiltonian.
I see.
And so I'm interested in this kind of constrained optimization problem. What is the most
Understood.
entanglement I can have of fixed
Oh,
energy?
I see. Thank you so much. Yeah.
Yeah, thanks for the question. Okay, so let me give you a bit of background here. So on what is known and what is often believed to just be, well, basically the standard law. So at finite energy densities, one typically expects that you can construct quantum states that have volume law entanglement entropy. So just to set up a bit of notation, because this is going to provide a reference point. Suppose first off that, if I had some thermal state at temperature T with respect to Hamiltonian H, so this thermal state, is defined in this way. I'm going to write its energy as E as some function of temperature and its thermal entropy as S with this superscript H. It's the von Neumann entropy of this quantum mixed state. And so That's just as a notation. Let's talk about pure state entanglement. So the earliest work on entanglement in many-body pure states goes back to Don Page in the early 90s, who showed that if you take a typical pure quantum state of n qubits, then the half-system entanglement entropy scales with the volume of the system. Okay, so in particular, it's going to essentially be the log of the total Hilbert space dimension. So you could think of that as the exponential of the infinite temperature thermal entropy. If you go to states that have finite energy densities, talk about typical states with finite energy densities, what one often says is, well, the thermal entropy can be viewed as a kind of logarithm of some effective Hilbert space dimension. And if you want to think in those terms, your first guess would be that if you have a quantum state that has some energy E, which I can associate with the temperature, that's defined through the Hamiltonian. My first guess would be that the half system entanglement entropy is just going to be half of the thermal entropy of the whole system up to some corrections. Okay? So this kind of basic thermodynamic reasoning actually it turns out to be pretty good at finite energy densities, and provides actually the basis of our understanding of eigenstate thermalization. Okay, so this thermodynamic reasoning obviously fails when you go to ground states for a reason that will become clear in about 2 seconds. So yeah, so let's suppose that's finite energy densities. At finite energy densities, where I have some energy that is the ground state plus something that's scaling with the total system volume, I expect that my typical quantum states will have half system entanglement set by the thermal entropy. But if I go to ground state at zero energy, energy EH0, I'm calling it, then of course the thermal entropy with respect to the Hamiltonian is zero, but the ground state could still be entangled. So it's obvious that I can't relate the thermal entropy and the ground state entanglement entropy in this case. And the point is basically that there's no kind of product state basis at low energies. This is one part of the problem here. There are clearly many problems with trying to apply thermodynamic reasoning in this setting. Um, but what I kind of want to understand is how it is that we cross over to this thermodynamic way of understanding entanglement as we increase the energy. So what I'm going to show you is actually that there is a mapping to thermodynamics that allows you to understand entanglement at all energies, not just at finite energy densities. Okay, so and one last kind of part of the setup. So another reason you might care about trying to calculate entanglement at fixed energy is that you might want to know how hard it is to predict a response function. So one way you might try to predict a response function is to represent some ground state on a classical computer, say using a tensor network, locally perturb the state, and then let it evolve in time. Okay? And now the perturbation here is injecting some finite amount of energy. And so what you'd then be interested in is how entangled the state could possibly become under the constraint that it only has energy of order 1. Okay, so now that's the setup. Now onto the math problem. Okay, so I'm thinking about a geometrically local Hamiltonian for a bunch of spins. My Hamiltonian here can be written as a part acting on this region A, which is approximately half the system on the left, and the kind of boundary region B, which separates A from C. My Hamiltonian can be written in the form of a sum of two terms. There's a part acting on AB and a part acting on BC, where these two terms do not commute with each other. The only constraint that I'm going to impose for my general results is geometric locality, which is just to say that I can split my Hamiltonian into these two terms. Now, what I'm interested in is the object on the left. So the notation here means that the thing above max is the thing I'm optimizing over, and the thing below is the constraint. So I just want to know what is the maximum possible half-system entanglement entropy, given that I have some energy expectation value E. So as I just mentioned, this teaches us about the cost of simulating quantum dynamics, and if you care about zero temperature response, you care about energy of order 1. So part of the reason for setting up the problem in this way is because it has a more than superficial similarity to a problem that we all solved as undergrads, or at least maybe we read about as undergrads. So the problem of maximizing von Neumann entropy, or more generally, Shannon entropy in the classical case, at fixed energy. Okay, so let's talk about this other related and much simpler problem for a moment. So suppose I didn't care about maximizing the entanglement entropy of A at fixed energy. I just wanted to figure out the maximum possible entropy of the whole system, ABC, uh, subject to the constraint that I had a fixed energy, right? So the solution to this has been known for a very long time. It's the Gibbs state. So the state that maximizes the entropy has this functional form, and the temperature here is just a number that you choose so that you satisfy the constraint on your initial state, on your state in the initial problem, sorry. So let me just highlight some technical differences relative to our problem. So first off, we're trying to maximize a local entropy, so just the entropy of a large subsystem A on the left, subject to some global constraint on the state, which is expressed in terms of the Hamiltonian for the whole system. And the other point is that the overall state of the system is pure. And this is important because otherwise SA is not an entanglement measure. Okay, so my approach in the following is just going to be to relax this difficult entanglement maximization problem until it turns into a much simpler thermodynamics problem where I know the answer. So the question is, what is the form of the thermodynamics problem that I map to? So to get some intuition for what I'm going to end up at, ignore the Iraqi-Lieb inequality for just a moment. To get some intuition as to what I'm going to end up at, let's just remember that, well, A can only be entangled if BC is also entangled, right? So this sort of suggests immediately that if there is any thermodynamics problem hiding here, then it should look like the sum of entropies of something on the left and something on the right. So in order to get to that object, that sum, let's first off relate our entanglement entropy on the left using some simple entropy inequality to a sum of two other entropies. Okay, so we have the sum of von Neumann entropies of these overlapping regions A, B, and BC. And the fact that there's an AB and a BC here and an AB and a BC over in the Hamiltonian is going to be important in just a moment. So a lot's going to happen on this next line, so we can talk about that for a moment. What I now want to do, instead of maximizing the left-hand side of my inequality, is maximize the right-hand side. So this red thing is just coming from the dimension of B. So I want to maximize the sum of SAB and SBC subject to some constraint on the NG expectation value. But so this is still pretty hard. And the reason it's still pretty hard is that there's this other kind of very nonlinear constraint hiding in the problem, which is that this quantum state psi has to be a valid quantum state of the whole system. The fact that we're talking about actual quantum states here is really the problem. And as a consequence, we can't think of this as maximizing the sum of two entropies. So what I want to do is to relax my optimization problem, allow myself to optimize over states that are not necessarily physical, but which have physical states as a subset. And I have to do this in a very specific way. I have to relax my optimization problem while still being able to express my constraint. That is probably a little bit tough to understand before seeing what you do. So this is how you do it. So what you should imagine now on the right-hand side is that I have two density matrices, one for AB, it's called sigma AB, another for BC, it's called sigma BC, but I'm not going to constrain these density matrices. They're totally valid density matrices for AB and for BC, but I'm not going to require that they're consistent with each other. So there doesn't have to exist any state of ABC of which these two things are both reduced density matrices. Going to this specific relaxation is really important because we can still express our constraint on the energy as indicated below here. So the expectation value of the total Hamiltonian in our state is the sum of the expectation values in these two terms, AB and BC. But I can still write that down in terms of these new states, sigma AB and sigma BC.
Sorry, there is a question. So can I ask that if this inequality can only be saturated if sigma AB and sigma BC are consistent with some certain global state?
It is certainly saturated in that case, but it may be saturated in other cases.
Okay, I see. Thanks.
Any other questions about this point? Because this is maybe the most, I mean, it doesn't get much more technical than this, actually. Okay, so the next step is now just to see that the right hand that you already know the solution to the right hand side of this inequality. So on the right hand side, because sigma AB and sigma BC are independent of each other, all I'm now saying is that, well, what I'm trying to do is maximize the sum of the entropies of these two separate systems, subject to the constraint that the sum of their energies is E. But we know the answer to that. You're just supposed to put these two things in thermal equilibrium and put them at the same temperature as each other. That's it's sort of how you define temperature in thermodynamics. And so that leads us to the upper bound. So the upper bound on entanglement is just going to be half the sum of these two thermal entropies. And I'll introduce a diagram in a moment to explain what this sum means. So first off, left-hand side, here's our original problem. It's a many-body system that has a Hamiltonian consisting of two non-commuting terms. And on the right-hand side, well, we've sort of doubled the B degrees of freedom. So on the right-hand side, there's one system called AB, and that has a Hamiltonian called HAB. And there's another system called HBC, acting on a system called BC. And another point here is that, of course, the original Hamiltonian will involve some terms that only acted on B, and I'm free to kind of split them up however I like. So maybe I put half in HAB and half in HBC. So what you're supposed to do now is say, well, I have some pure quantum state, and I know its energy expectation value. It's E. Now, what I want to do is figure out at which temperature I should put my fictitious thermodynamics problem. On the right-hand side, we imagine these two separate systems, each in a thermal state at some temperature T star. And the T star is determined by a very simple condition. It's just that the sum of the thermal energies of these two separate fictitious systems should match the original energy that was in my constraint. That's kind of it. So I pick an energy, I convert that into a temperature by just asking at which energy would these two systems in thermal equilibrium have the same temperature. And then I compute the sum of the entropies of these two systems at that temperature. And then there's an area law contribution which vanishes in lots of systems you might care about. So if you have reflection symmetry, for example, you can just kind of get rid of that area law contribution. Okay, I always get lots of questions about this point, so I'll pause for a minute here.
And so just to check, so in the previous in the optimization question, so sigma AB and sigma BC are independent, right? So we know to put them both in some Gibbs state, and here you've set them to be the same temperature. Is that obvious or in
Yeah,
principle?
yeah. So this is yeah, right. So this is it's sort of how you define. Okay, it's how I was told that you define temperature when I was young. So the you take two systems and you ask what property you can do this rigorously. You say, well, if these things are in thermal equilibrium, there should be some number that they share, and that's temperature. And you sort of design temperature that it has this property. But more formally, what you can do is you can just say, well, I have two systems and I want to maximize the sum of their entropies subject to a constraint on the energy expectation, subject to a constraint on the sum of their energies. And then what you'll find is that the solution to this problem, this optimization problem, is to set their temperatures equal to each other.
I see. Right. So in principle, T1 and T2 were just anything that satisfies total energy to be E, but you find out that T1 must be equal to T2.
Yes, that's the solution to the optimization problem.
Yep, understand. Thank you.
By the way, I happen to be teaching this class.
Yes.
It's something I taught before.
Right. Okay, as I found out while writing this paper, unfortunately, such a simple condition does not hold when you do Renyi thermodynamics. But I will derive some slightly more complicated bounds. Oh, in the paper, we derive some slightly more complicated bounds for the analogous Renyi entanglement measures. These generally take a horrible form because the temperatures of the two systems, the kind of Renyi temperatures of the systems don't match. But if you have reflection symmetry, they get very simple again. So this statement about the von Neumann entanglement entropy upper bound is very simple. It's just this thermodynamics problem. And although I'm not going to show this until the final slide, there is an analogous upper bound on Renyi entanglement entropies, which also looks very simple if you have reflection symmetry. just to kind of about B. Okay. So the next point is actually there's another thermodynamics problem that provides you with a lower bound on this maximum entanglement entropy. Again, much simpler when you have reflection symmetry. So I can talk about the details if you like, but I'm showing it here just to demonstrate that the upper bound is optimal up to area law corrections in systems that have conventional thermodynamics. So on the right-hand side, our maximum entanglement is upper bounded by the sum of thermal entropies of these two systems. On the left-hand side, we have another thermodynamics problem that differs from the one on the right only in its boundary conditions. So then the point is that if you have a quantum system whose thermal entropy is dominated by its bulk rather than its boundary, then both the lower bound and the upper bound are going to scale with the system size in the same way. So you see that the bound is optimal. The catch is that you can only prove this lower bound in reflection symmetric systems.
Sorry, what is this lower bound again?
Yeah, so the upper bound, I was saying that so I take the maximum entanglement entropy of my state at fixed energy, and I was saying I can upper bound this by a sum of thermal entropies. So if I can also lower bound this quantity by a sum of thermal entropies, but the sum of thermal entropies are now, or the thermodynamics problem is now defined in terms of different Hamiltonians. But those Hamiltonians differ from the ones on the right-hand side only in their boundary conditions.
Yeah, but I'm asking what is the other thermodynamic problem?
Oh, I see. Okay, yeah, sorry, let me go into that in detail. So, okay, imagine I have a reflection symmetric system. So A looks like C. So this is used, and then what I'm going to imagine is that I impose, so maybe just as a starting point, because this is the maximum entanglement entropy, I can lower bound this object by just computing the entanglement entropy of any state that has any GE. So I'm just going to pick a state that has any GE, and then I'm going to insert it into the entanglement entropy, and I'm going to pick it. And basically, what I have to do is choose a state, a pure state of the whole system, um, that has a special property, which is that its half system entanglement entropy is also the sum of thermal entropies. So what you should imagine is that you kind of freeze the B degrees of freedom. So I'm choosing a pure state. I freeze the B degrees of freedom. Having picked some state for the B degrees of freedom, imagine it's a product state. I then construct an effective Hamiltonian for the AB region, which basically involves taking the original Hamiltonian for AB, this HAB, and sandwiching it between the pure state phi that I've put on the B degrees of freedom. This gives me some Hamiltonian for the left. I do the same on the right. And then what I construct is something that looks a bit like a thermofield double, but shared between A and C. But that thermofield double is defined with respect to these kind of effective Hamiltonians that I got from kind of locking the B degrees of freedom.
I see. Thanks.
So yeah, the catch is you can only show that the lower bound only exists when there exists an energy of this thermodynamics problem that can match your constraint. And because you've done something strange to the boundary condition, it ends up meaning that you can construct this lower bound only when the energy exceeds an area law scaling. So, energy is larger than L to the D minus one here, where L is like the system length and D is dimension. Okay, any other questions about this point?
Uh,
I
hi-
guess I'm still a bit confused. Why does it only apply to this particular energy? My understanding is that now I'm fixing the states in B, but still I have HA and HC. In principle, the energy coming from HA and HC can scale as the volumes of HA and HC.
Sorry, I was unclear. So this notation is to say that E is like larger than L to the D minus one.
I
E is
see.
at least L to the D minus one. Anything above L to the D minus one is fine.
Mm-hmm. And in this case, the lower bound in the left side is still some kind of thermodynamic entropy. Is it?
Yeah, yeah. So it's still a thermodynamic entropy because I chose a very special pure quantum state that looked like a thermofield double.
Mm-hmm. I see. Thanks.
Yeah, thanks for the questions.
Hi, I have a question. I just wonder how you are defining reflection symmetry, like in higher dimensional lattices.
Oh, I see. So yeah, it's about the sort of play. It's through B. So imagine that I can choose B to be a sort of single plane or two planes, whatever I like, so long as A and C are separated from each other. And here, really, what I need is that the Hamiltonians for AB and for BC are isospectral. That's really all I need. But I get that for free if I have a reflection symmetry about the plane defined by B.
Oh, I see. I see. Thanks.
So now that we have these bounds, we can just start asking, well, what do my thermodynamic properties of the system imply for the entanglement of low energy states? So let me just show you how the machine works. So I'm going to throw in some specific heat capacities, assuming that such a thing exists, and then spit out some upper bounds and entanglement. And so here, what I'm going to do is, for simplicity, show you the results when I allow my energy to scale as L to the T minus one. So area law scaling of energy. So let's say I had a gapped system. In a gapped system, you generically find an essential singularity in the specific heat. And when you throw this into the bound, you get an upper bound on the entanglement entropy that is area law with a logarithmic correction. This has a very simple interpretation that I'll describe in a couple of slides. If I threw in the heat capacity of a Fermi or a Luttinger liquid, I'd find some temperature T. Then I would get a violation of the area law not by log L, but by square root L. The point is just that if you have this large low temperature specific heat, it means there's lots of low energy states. And because there's lots of low energy states, it's possible for you to construct some highly entangled thing at low energies. And if I thought about a quantum critical system, say with a dispersion going as wave number to the power of z, z is the dynamic critical exponent, and in spatial dimension d, then I would find an area law violation by this kind of more exotic exponent. So what I want to highlight here, though, is that the exact energy constraint is not really important so far. And there are some other methods which you can dig out of this paper from Fernando Brandao back in 2015 that could also be applied. However, capturing the constraint on the energy exactly, which is why I was so careful about my boundary conditions, is going to become absolutely essential for understanding why these highly entangled ground states are so weird. So this is, a lot of text in a table. It's nicer to have a kind of graphical illustration of this. So yeah, here's the kind of general result summarized for a variety of different heat capacities. At the bottom, we have the gap system. We have a small specific heat at low temperatures, and consequently a small upper bound. When we go to, say, some quadratic dispersion, we get a larger upper bound. And then when you go to the something with, it keeps increasing basically. So as another example that I find quite interesting, so there are certain quantum systems in one spatial dimension that we know of, random quantum spin chains described by the strong disorder renormalization group, where one finds a specific heat that's very large at low temperatures, this kind of logarithm. So this inverse logarithmic scaling is coming from the fact that there's an enormous number of these kind of delocalized low energy degrees of freedom. And it ends up meaning that even at sub-extensive energies in these systems, there exist states that are almost volume law entangled. They're volume law entangled up to just a kind of log correction. And this is pretty strange because that's very far from what the ground state looks like. The ground states are kind of slightly entangled. They're logarithmically entangled. But what this is saying is that there's so many low energy states that you can create this very complicated superposition that is almost volume law entangled. If you take
So,
the strong disorder renormalization group literally.
is this for a given sample of the disordered system, or is it some disorder average?
Yeah, okay, good question. So I think the heat capacity is expected to be self-averaging still in this case.
Mhm. So, am I understanding correctly? Here, the statement is that given a particular pattern of temperature dependence of the heat capacity, then you will be able to predict this maximal entanglement entropy.
Exactly. Yeah.
Mhm.
So you just throw in a specific heat and you get upper and lower bounds in entanglement.
I see. I have the impression that in one of Brandel's papers, they said that even for gapped system, that the heat capacity has this exponential decaying form has not been rigorously proved.
Capacity others. So in which system, sorry? In
Gapped.
In gap system, the fact that the heat capacity has this e to the minus delta over T, you mean?
Yeah, they said it's not rigorously proved.
Oh yeah, for sure. Yeah, yeah, and I'm not pretending to prove it here. So I'm wanting to. I'm going to throw this in as an extra assumption. So we
I see.
do not know for sure that the specific heat has any of these forms. So we're not proving that. It's that assuming thermodynamic properties, then we can prove something about entanglement.
Okay, thanks.
So yeah, okay. Thanks for the clarification for the question, the clarification there. So the kind of broader aim here is to understand how it is that imposing what I would call physical properties on a many-body quantum system constrains the complexity of that system. So, for example, we know that you can encode the solutions to hard computational problems in ground states, but probably your transverse field Ising model didn't do that. So the aim here is to ask, if I just demand that my system has sensible thermodynamics, is it still complicated? And here I'm addressing that by studying entanglement. But yeah, so I have this is really an assumption.
Okay, thanks.
Okay, so let me briefly give you a kind of understanding of what's going on for gap system because there it's really simple. Let's say I just had a bunch of spins, and then I consider the dimension of the space that has some integer amount of energy E. So I'm thinking about like a microcanonical window here. In particular, I'm thinking about the space of states spanned by dilute spin configuration. So I have these um, very rare down spins at some vanishing density, and then I know the dimension of this space just from combinatorics. And then you could ask, well, what is the entanglement of a random state in this space? But what you'll find is that a random state in this space has an entanglement entropy that scales as L to the alpha times log L, which is exactly what we find in the upper bound for gap systems. So this is an additional confirmation that the bounds are optimal. Okay. And yeah, so roughly what I'm saying here is that if you because we're now thinking in thermodynamics, it gets very intuitive and I think a bit less mysterious. You throw in energy E, so you have a gap let's call it delta. You can create E over delta excitations. Each one of them can be in L to the D possible locations. And so each will contribute an amount of entropy that's just log of volume. So you just have log of volume for each one of your excitations. That's all that's going on in the upper bound for gap systems. Okay, so let's get back to these kind of very strange local Hamiltonians that are highly entangled ground states. So these are important, as I mentioned before, because they are counterexamples to the idea that low energy should mean low entanglement. So just running through the examples again, we see there's lots of powers of L appearing on the right-hand side here. These are all violating the area law, possibly with log, the area law asterisk with log corrections conjecture. But the nature of a counterexample is that you have to be able to construct it. So then you have to ask yourself, well, what was the special feature that all of these models had that allowed for the entanglement to be calculated? And the feature of these Hamiltonians that allows them to be solved is that they're all frustration free. So frustration-free Hamiltonians, let me just remind you, you should imagine you have a local Hamiltonian. It's a sum of terms called Hj, and your ground state is a ground state of every term individually. Okay, so there is no frustration because you satisfy every single term in the Hamiltonian. But thinking about frustration-free systems, it's interesting because these things are highly entangled. It's also interesting because some of our what we know about area laws in dimension above one is all based on frustration-free systems. So I mentioned before that the area law has been proved for translation invariant 1D spin chains with a gap. In 2D, the best result in this area so far is to show that if you have a frustration-free two-dimensional spin system and a so-called local gap condition, this means that any kind of contiguous sum of plaquette terms in their Hamiltonians are gapped. Then you find area law. So this is a very nice result. There's another result in this area which applies to a more restricted set of Hamiltonians. So it's qubits with a special kind of nearest neighbor interaction. It's still frustration free. Actually, it's in general dimensions. This is work from Jens Eisert's group in 2010. So what they were able to show here is actually, without assuming anything about the spectral gap, they found area law, which is, it seems pretty weird in the first instance. Like it doesn't matter at all what the gap is, you get area law. So let me just first off explain why that's not surprising, and then and the reason it's important to focus on this example is that I'm going to generalize this kind of idea to very wide varieties of systems. So the reason you shouldn't be so surprised by this is just that the Hamiltonian of a frustration-free system has a kind of it's a kind of symmetry. So so if I take my Hamiltonian that was originally a sum of these just HJ terms, these kind of local terms, then because the ground state with the ground state of every term, then I can rescale all of those terms by positive numbers without changing the ground state. So I can do this without changing the ground state, but of course, in general, I'm going to change the spectral gap. So this is just a kind of justification for why you shouldn't be too alarmed by area laws without spectral gap assumptions in frustration-free systems.
Okay, can I ask a question that may not be directly relevant? So suppose we have two local Hamiltonian, two gapped local Hamiltonians, and we know that they have identical ground states.
Mhm.
Then is it guaranteed that there's a adiabatic path, meaning a family of four no gapped local Hamiltonians that can continuously interpolate these two Hamiltonians?
So sorry, you have so two Hamiltonian same ground state.
Yeah, are they adiabatically connected?
Um, that is so, and you want to define adiabatically in terms of no. Uh, I think no. I'm sure I could construct a counterexample. So you'd think that you could take Hamiltonians that like have because you're asking about a relation between the whole Hamiltonian, right? But I could easily cook up examples where maybe the ground state is just say all spins down, and then there's something crazy going on at high energies. So yeah, let's see. So if I took okay, let's get into this at the end because I think the example that I'm going to use is actually also going to the Hamiltonian will appear later. But yeah, it's a good question. I'm okay. I'd be really surprised if you couldn't cook up a counterexample to that.
You will be surprised if I can or cannot.
I'd be okay. Let's see. So you say same ground state. You have two Hamiltonian. You okay? So you take the family of all Hamiltonians that have a fixed ground state, and you ask if you can adiabatically transform between all of these Hamiltonians.
No, I have two Hamiltonians which have the
Hmm.
same ground states. Both of them are gapped and local. I'm asking whether there's a family of Hamiltonians uh, which are all gapped and local that can continuously interpolate them.
I'd have to think about it. Okay,
Mhm.
let's come back to this later.
Yeah,
But yeah,
thanks.
thanks for the question. So yeah, sorry, I'm gonna get stuck on that if I think about it for too long. So yeah, we'll come back to that at the end. Right. Okay. But so just to summarize where we were a moment ago. So we're thinking about what I'm going to do is generalize this kind of idea that you can get area laws without assuming anything about the spectral gap. The argument isn't it's going to turn out to be really simple when we're actually in the ground state manifold. But what's nice about it is it's going to extend all the way up to finite energies and finite energy densities. So, okay, I'll show you the ground state version of this. So let's call it it's a relation between entanglement and ground state degeneracies. So here's our original thermodynamics problem. We got the entanglement entropy of subsystem A subject to some overall constraint on the energy expectation value. And what I want to do is think about my frustration-free system. For simplicity, I'm going to break up my, my Hamiltonian that was acting on B into one on the left, one on the right. And a really important property here is that because the Hamiltonian is frustration-free, the ground state of the whole system is also the ground state of any patch, right? So HAB, which only acts on this patch on the left, um, annihilates the ground state. So what that means is that if I set that the energy is zero in my constraint, what that means is that the effective temperature of my fictitious thermodynamics problem, that's also going to be zero. The reason that's nice is it just tells you that the entanglement entropy of subsystem A is upper bounded by the ground state degeneracies of HAB and HBC, these kind of overlapping systems. So this is pretty intuitive. It's just saying that you should figure out how many ways the system can be in the ground state on the left and how many ways it can be on the ground state on the right. And it can't be more entangled than the number of possible ways it could have been the ground state on both sides. In fact, we can make that much more concrete. So let's go to thinking not just about entanglement, but all von Neumann entanglement, but all Renyies, including Renyi 0, where we're really just talking about Schmidt rank. So now this linear combination of entropies can be upper bounded by these ground state degeneracies. Okay. So now let me just, this maybe looks a bit unintuitive. How should we expect DAB, which is the ground state degeneracy of HAB, to behave, this thing here, the degeneracy? Let's look at a slightly funny Hamiltonian just to make a point. So let's imagine my Hamiltonian consisted of a bunch of these kind of funny plus shapes. So if they consisted of all these plus shapes, and notice that the B region here is 2 sites wide because A can't talk to C. Then when I construct my mapping, when I construct HAB, I take those spins, and of course, this Hamiltonian still involves these plus shapes, but now at the boundary, there are going to be missing terms. So because of these missing terms, there are going to be some degrees of freedom that are not really pinned in the ground state. They can just do whatever they want. It's like I have extra spins that I'm not constraining. Now, because of all these loose degrees of freedom at the boundary, what you'll generically find is that the degeneracy of HAB will scale exponentially with the surface area of this patch, which is the left side of the system. And so what that will give you is then areolar entanglement. So the statement here is actually really simple. I'm just saying that if you take if you take a frustration-free many-body system, and that system has what I would say is a well-behaved thermodynamic properties in the sense that the zero temperature thermal entropy does not scale with volume and scales at worst with the surface area, then you find areolar entanglement. So this first statement that when you go to zero temperature, the thermal entropy is not too large is typically known as the third law of thermodynamics. Many different interpretations exist. So here I'm going to use an extremely relaxed interpretation of the third law, which is that the zero temperature thermal entropy is only allowed, it can't be larger than L to the D minus 1. It can't be larger than the surface area, meaning no extensive number of loose degrees of freedom. In frustration-free systems, this thermodynamic statement implies areolar entanglement. Okay, so I'm coming towards the end now.
Sorry, but you are not proving the third law, right?
No, absolutely not. So it's the same structure as before. I'm assuming thermodynamic properties and asking what these assumed thermodynamic properties imply for entanglement.
Thanks.
So yeah, this is a very different strategy to what's kind of common in this very, very vast mathematical literature that aims to prove area law from a spectral gap assumption. So the spectral gap assumption is, clearly an energetic assumption, right? You say, suppose the system is gap, am I area law entangled? And there's been, a huge effort over 2 decades now trying to prove area law entanglement in 2D, which unfortunately has not succeeded, except in frustration-free systems. But what I'm saying here is that, okay, well, also in frustration-free systems, without really assuming, you can throw away the energetic assumption. Just assume that you have the assumed third law of thermodynamics, then you get areolar entanglement. So it's coming at this from an entropic assumption rather than an energetic assumption. Okay, so let me just now go through a couple of examples to kind of illustrate what's going on here. So let's talk about something really familiar, the AKLT chain. So we're thinking now about a chain of spin ones. This is a frustration-free Hamiltonian. With periodic boundary conditions, you have a unique ground state, and with open boundary conditions, your ground state is instead fourfold degenerate. So let me just sketch this. The dot, dot, dot means I have periodic boundary conditions. It wraps around. B is this buffer between A and C. And so what I want to do now is, compute my upper bound. So I need to figure out the ground state degeneracy of the Hamiltonian HAB, similar for BC. So let's look at the Hamiltonian for HBC. So that Hamiltonian, it's just an AKLT chain, but with open boundary conditions. And therefore, its ground state degeneracy is 4. And as a consequence of this, I find an upper bound on the Renyi entropies that is 2 log 2, which is actually saturated in the AKLT chain. Okay, that's a fairly familiar but pretty weakly entangled state. Now I want to give you some insight into how it is that these counterexamples to the area law with log correction come about. So I'm going to talk about the Motzkin chain. Actually, in spite of my advertisement that I'm going to talk about the most highly entangled states, for simplicity, I'll actually talk about the colorless Motzkin chain just because it will provide a simple way to explain the mechanism. But the mechanism that I'll describe, the mechanism by which this system is entangled, is also well, it's a simple version of the mechanism by which many of the other states that I mentioned earlier are highly entangled. So basically, by understanding this example, you can figure out what's going on in most of the other examples. So what we're thinking about now is a chain of spin ones again. It has these nearest neighbor projection terms. This is some rank 3 projector onto a bunch of highly entangled states, or maximally entangled kind of pairwise states. And then there are these boundary fields, okay? So this Hamiltonian, which looks pretty sensible. I mean, it's just like it's a spin one system. This is some spin one, but this is a two body interaction on nearest neighbors. This thing with two body interaction on nearest neighbors has a unique ground state, and with these boundary conditions, it has logarithmic entanglement in the ground state. So I mentioned this is the so-called colorless Motzkin chain. The colorful Motzkin chain involves higher spin terms, say like spin 5, spin 3, spin 4, and so on. And actually, I might be getting those exact numbers wrong. So anyway, the higher spin, maybe it's spin 2 and higher. But the point is that when you have these additional when you have higher spin in this case, you can start using a similar construction, including crucially these boundary fields, to create these ground states that have square root L entanglement. Okay, so why are they highly entangled? So a really important point is that if you take any of these models, colorless or colorful Motzkin, and you remove one of the boundary fields, then the ground state degeneracy is no longer one, it is of order the system length. It is volume law scaling of ground state entanglement. So this is non-third law-like in my notation mentioned earlier. So then if I look at the Hamiltonian of AB, so this is like part of the Motzkin chain, but it's missing one of these boundary fields. And because it's missing this boundary field, because it's missing the right boundary field, it has a large ground state degeneracy. So because of this large ground state degeneracy, you find an upper bound on entanglement that's, in this case, it's only logarithmic, but the same mechanism leads to a power law in the colorful Motzkin chain. So just to summarize this point, because I was going into quite a few details here without fully introducing the model, the only way that a frustration-free ground state can be highly entangled is if it is built out of terms that have huge ground state degeneracies. So the point is that there are lots of ways you can be in the ground state of the left of the chain, and there are lots of ways you can be in the ground state of the right of the chain. And it's having all of these kind of extra degrees of freedom to work with that allows you to construct a Hamiltonian for the full chain, where the ground state is unique, but where there's a lot of ground state entanglement. So this is pretty strange, right? It's highly entangled, but really the boundary conditions are key. And this is not something we usually think of as boundary conditions are usually something we think of as not having a huge effect on many-body quantum systems. So this is I would say, a slightly unphysical feature of these models. Okay, so kind of just to wrap up, I was going to give you one last very familiar example. There's one slide, and I got into the Outlook. So let me now just give you an example, taking you all the way from the ground state to finite energy densities in a very familiar model, which is a Heisenberg ferromagnet. So okay, if you weren't familiar with the Motzkin chain, don't worry. We're now just talking about a bunch of spin 1/2s that want to align with each other. We have SU2 symmetry. That we can be on a line, on a square, or on a cube, whatever you like. And the frustration-free ground states in this case, it's frustration-free. The ground states are basically all spins up and rotations of that state. The number of distinct ground states related by rotation is L to the D. And so what you find is a ground state entanglement entropy that's no larger than L to the D. This is because you could construct some crazy superposition of all of the different classical looking ground states. And then what you'll find, that's zero energy. And now what I want to do is apply this result at finite energies. The nice thing about frustration-free systems is I can apply my bounds all the way down to the ground state, whereas more generally, I can only apply them down to energies that are of order L to the D minus 1. So here, I'm going to choose my dispersion to be, not choose, sorry, that's already given to me. The dispersion is k squared because it's the Heisenberg ferromagnet. What that means is that the specific heat follows this power. And so now what I'm going to show you is the form of the upper bound on entanglement entropy at low energies. So this works all the way down to E equals 0. So yeah, so what I find is pretty simple. It's just this kind of ground state term And then on top of that, I have some term that grows as a power of the energy and with the system volume. And this exponent 2 and 1/3 is all coming from the mapping to thermodynamics that I mentioned earlier. So what I think is pretty neat about this is you see that there's the upper bound on the entanglement can clearly be split into two terms, one from the ground states and one from the excitations above the ground state. And you see that actually already at energy of order 1, the excitations dominate the entanglement entropy that you can have at low energies. They dominate the upper bound. Okay, so um, I think I have another slide actually on numerics, but I'll skip that and we can come back to it if you're interested. Let me now just go to the summary because I've hit time. So what I've described are some upper and lower bounds on the maximum possible entanglement that quantum states can have at a fixed energy. I'm going to now show you the most general form of the bound in reflection symmetric systems, which applies for all Renews. So the right-hand side is the solution to a problem in what I call Renyi thermodynamics, which is where you think about the states that maximize Renyi entropy is subject to an energy constraint, rather than the states that maximize von Neumann entropy is subject to an energy constraint. Bound takes the same form as it would for alpha equals 1, which we discussed. And I've also talked about how when you're thinking about ground states of frustration-free systems, you can just know the zero temperature thermal entropies of subsystems and import those into your problem. And basically, by assuming some thermodynamic properties, you can upper bound ground state entanglement. And now for frustration-free systems, you can sweep all the way down to the ground state. So, this is the third law implies area law statement I mentioned. And so where does this all lead? So as I mentioned earlier, the kind of broad problem here is to understand how we can impose physical properties on the class of all possible local Hamiltonians to exclude those that we maybe do not consider to be physical, and hopefully to understand in a bit more detail what it is that makes low energy quantum matter computationally hard. So I indicated this earlier, but I'll say it again. It's unlikely that physical condensed matter systems, encode the solutions to hard computational problems in their ground states, unless they're spin glasses and so on. So in particular, I doubt that two-dimensional magnets really, when you get into the ground state, is performing some 1+1D quantum circuit in space. So one kind of immediate question raised by what I've been saying today concerns these local Hamiltonians that do have highly entangled ground states. So because they have highly entangled ground states, they must have strange thermodynamic properties. So it'd be pretty interesting, I think, to figure out, for example, the thermodynamics of the Motzkin chain, or more generally, the thermodynamics of a Hamiltonian that you get through the circuit to Hamiltonian mapping. So this is a kind of rough indication of what would happen in Motzkin. And then a final question, which is a bit more speculative. So there's been a lot of recent work on the construction of Lindbladians that have Gibbs states as their steady states. So these Lindbladians, when viewed as operators acting on a doubled space of kind of tensor product of Kettenbrauer, are often frustration-free. And so many of the techniques that I've described over the last hour or so could also be leveraged in that setting. And here there's potentially an opportunity to learn something about the operator space entanglement entropies of Gibbs states, and hence of the complexity of representing these states using tensor networks. Okay, thank you for listening and for the questions during the talk.
Yeah, thank you very much, Sam, for the very interesting talk. Okay, any further questions?
Hi, yes, I have a question. So maybe I can ask the question in a converse way. So if I really want to construct a model that where I have high entanglement in low energy, then what is the ingredient that I must consider? Maybe the frustration free is one of the key.
Yeah, so frustration freeness, I don't know if it's necessary, but frustration freeness allows you to make analytical progress. And so basically, this was my point, that if you're going to construct a counterexample, you sort of have to be able to, construct it. And so you need some feature of the problem that makes it tractable for you. And so frustration freeness is a natural one because it just, provides you an analytical way to construct these ground states. So yeah, what you want is to construct frustration-free ground states that have the following property. the left side of the system has an enormous number of ground states. The right-hand side of the system has an enormous number of ground states. When you couple the two together, there is only one ground state.
Ah, I see.
The point is that the ground state of the full system then ends up being some superposition, some superposition of all of the possible ground states of the two halves.
I see. And sorry, but I'm still a bit confused. Do you mean that the frustration-free Hamiltonians are relatively fine-tuned, such that most of the Hamiltonians have low entanglement into energy?
Yeah, so I think the example, yeah, so I think, well, frustration, yeah, even within the family of frustration-free systems, I think that the frustration-free systems that have so far been constructed and that have highly entangled ground states are fine-tuned. Yeah, I
I
don't
see.
think that kind of entanglement. I've yet to see any non-fine-tuned Hamiltonian. I don't know how to, the thing is, fine-tuning is such a loose concept that I don't know exactly how to describe this point. But I think if I just picked a random two-dimensional quantum Hamiltonian, sorry, random Hamiltonian for a bunch of spin-1 halves, let's say, I don't think I would find that it had a highly entangled ground state.
I see. Thank you very much.
Sam, I have a follow-up question. Now suppose I start with this Motzkin Hamiltonian, which has the feature that the left-hand side has a lot of degeneracy, the right side also has a lot of degeneracy, and when I couple them, there's only one degeneracy. Now suppose I add a weak perturbation, weak local perturbation. I would expect the left and the right-hand side will both only have some normal degeneracy, not that big, right? But maybe there will still be many, many no-line energy states. Then does this mean, or maybe although the ground state entanglement entropy is small, but maybe something like the integration of entanglement entropy among some energy window near the ground state will still be much larger than many other models.
Right, yeah, I think that's what happens. So in Motzkin, even if we didn't introduce a perturbation, let's say let's say we take Motzkin with no perturbation, then if I go to like energy that is of order like L to the minus 2 roughly, then I sort of get access to all of the would have been ground states. So let's say I didn't have my boundary terms in there, on the edges of my system, then I have this huge number of ground states. And you should think of, and there's huge subspace, and then you bring in these boundary terms, and what you find is that lots of these ground states get lifted to be just above zero energy. Um, but then, yeah, things get kind of tricky because then if you introduce an additional perturbation, like a field on one site, let's say, you start mixing these things together. So on the introduction of this, maybe local fields everywhere, so it's not super trivial, what's going to happen is that when you introduce local fields everywhere, you will end up with a ground state that looks like, if these fields are weak, a superposition of everything that was kind of in the low energy subspace of the original Motzkin chain. And what may happen, and what I would guess happens, but I can't say for sure, is that you end up with some gap, some aerial or entangled superposition of all of the possible Motzkin states.
Mm-hmm. But some of the no-line states still have rather high entanglement.
Potentially, yeah.
Mhm.
Yeah, it'd be pretty interesting to figure this out. I think very little is known about. There have been a few papers on this, but not so much is known about the excitations of Motzkin.
I see. Any other questions?
So I have a question. What causes the large degeneracies in frustration-free systems?
So it's not all frustration-free systems. It's particular families of frustration-free systems that people have constructed so that they have highly entangled ground states. And so I'm just saying that the mechanism for that family of frustration-free systems is that they've relied on some large degeneracies that have to be fitted together. So maybe the one way of thinking about this is as follows. So let's think about just a frustration-free ground state for a spin chain. So my frustration-free state is specified by just a bunch of constraints, right? So let's say on each pair of neighboring sites, I say, well, my ground state is in the it's in this subspace defined by it's in the subspace that is defined by the fact that it's annihilated by that term on a neighboring pair of sites. And it might be that imposing this constraint everywhere is not enough constraints. So my system gets forced into a still like large part of the Hilbert. It's in a smaller part of the Hilbert space than it was before I imposed any constraints. But there are lots of loose degrees of freedom left over.
Thank you.
Okay, any other questions?
So I think this method could be somehow generalized for other entanglement measures like mutual information or something, just like you have more partitions, like tri-partition or something like that.
Yeah, for sure. I've thought a little bit about this. So I mentioned before that the upper bounds were all coming really from maximizing the sum of two entropies of these kind of two overlapping regions. So I had these two overlapping regions, one on AB and one on BC, and I considered the sum of their entropies. And I was thinking about, the maximum of this sum subject to a constraint. So you can generalize this method to more patches. So the whole point is that you just need to make sure you can still capture your constraint. So let me go back about 100 slides so I can explain exactly what I mean by that. So give me just a moment. Right. Okay. So if you look at what's going on the inequality on the lower right here, then you can see that I had some constraint on the energy expectation value, and after kind of breaking up my system into this AB part and this BC part, then what I required is that I could still describe the constraint. So I can still write down that the expectation value is E, but by just expressing it in terms of the two other terms. So you can definitely generalize this statement to many, many different patches. But yeah, so far I've only been thinking about sort of positive sums. Whether it can be applied to mutual information, where of course you have, sum of two entropies, subtract the third one, is a very, very interesting problem. But yeah, not something I have a straight answer to right now.
I see. Thanks. Yeah.
By the way, Sam, in case you didn't know, Connor, the person who just asked you some questions, recently proved some nice theorems about mutual information and conditional mutual information.
Ah, right. Okay, really. Yeah, I'd be interested to hear about those. Yeah, please send me an email with the archive links.
Sure. Any other questions?
Yeah, sorry, I have another question. So does this method apply to fermionic systems?
To fermionic systems, you said, sorry.
Yeah.
Yeah.
Does this method apply to fermionic systems?
Yes, it does. Yeah, there's no. It's the same for fermionic and fermionic is easy. Bosonic is easy if there's reflection symmetry, but it's a pain if there is not reflection symmetry.
I see.
So the reason is just that extra term when I was using the Iraqi-Lieb inequality. So, but yeah, so if I have bounded local Hilbert space dimension, fermionic or spins, hardcore bosons, it all go through. The problem you run into is literally just the combination of no reflection symmetry and unbounded local Hilbert space dimension.
Yes. Thank you very much.
Mhm. Okay, any other questions? Okay, because of the limit of time, I think we should end the seminar here. But some maybe later I will send you some emails to ask some further questions.
Yeah, please do. Yeah. Thank you for all the questions, and yeah, I'm available by email, which I think is on my I think is available online.
Yeah.
All right,
Thank you,
thanks.
everyone. This is the
See you.
last seminar of the seminar series. See you next semester. Bye.
Thanks again for the invitation. Bye.